All right, good afternoon. Again, just looking into the test 3 review set of items, and we've looked at most of these already, but going back to what we have at the start of chapter 2, okay, we have for the first question, we have 3 items to deal with, and we have a given function, f of x is equal to negative 2x squared plus 16x minus 36. And we have for the first part is asking, does the function have a minimum or maximum value? And this is not a yes or no question, okay? It's going to be either a minimum or a maximum. And we have, in the case of the first item, okay, so we have this particular function given in standard form, and I want to translate this form into the vertex form, okay? So we have here, for the vertex form, we have a times the square of the binomial x minus h, followed by the addition of k. And now, and what we have for f of x equal to negative 2x squared plus 16x minus 36. Okay, so if I look at taking this standard form and putting in the vertex form, okay, so I'm going to start out separating the variable terms apart from the constants. Okay, so I'm going to put in parentheses the variable terms. So we have f of x is equal to the quantity of negative 2x squared plus 16x. And we have followed by the subtraction of 36. And okay, now I'm going to set things up where I'm going to complete the square, and before I do that, I want the first term in the parentheses to be just x squared. So right now I have the leading coefficient at negative 2. Now I could have already gone ahead and done this, but at this stage I'll just factor out the negative 2. So you have negative 2 times the quantity. So you have x squared, and negative 2 into 16x, this will be a negative 8x, followed by the subtraction of 36. And so I can double check here. So I got negative 2x squared, negative 2 times negative 8x is a positive 16x, and again I have minus 36. So I have the first term in the parentheses at x squared, and I'm going to make a squared trinomial with what is inside the parentheses. So I'm going to be entering the phase of the completion of the square. And again, doing this, I take the coefficient of the first order term, in this case which would be negative 8, and whatever the coefficient is, I'm going to divide by 2 and then square. So half of negative 8 is negative 4, and we have the square of negative 4 comes out to positive 16. And we have in the follow through, okay, so we have f of x is equal to negative 2 times the quantity. So we have x squared minus 8x, and we have followed by plus 16. And you have minus 36. Again, I want to keep things level with negative 2x squared plus 16x minus 36. And this is what I had before, but by adding 16, I'm adding not just 16, but negative 2 times 16. So I'm creating a bit of an imbalance. So by adding 16 inside the parentheses, the domino effect that is created at the front is going to be the change that we have in the amount of negative 2 times 16, which is negative 32. And I want to offset this deficit created by adding 32 at the end. Okay. And so we have in the rewrite, okay, so you have f of x is equal to negative 2 times the quantity, so you have x squared minus 8x plus 16, and negative 36 plus 32, again, we have at negative 4. Alright, so just sort of double checking here. Okay, so I want to keep this level with what we had before. So we got negative 2x squared. Negative 2, negative 8x will multiply out to 16x. Negative 2 times 16 is negative 32. Negative 32 minus 4 is negative 36. Okay, so I'm on track. And now, for what we're going to have in the result as I convert to vertex form. So we have f of x is equal to negative 2. And we have with this trinomial, again, this will be a perfect square of a particular binomial. So we have with x squared, okay, we have the square of x. And again, I had provided a change up by adding 16, and where does 16 come from? Again, it arose from having squared out negative 4. Okay, so that minus 4, or whatever value I square out in the completion of the square process, this will reappear in the binomial upon conversion to the vertex form. Okay, so I have negative 2 times the square of x minus 4, followed by the subtraction of 4. And now, just looking at what we have for a, h, and k. So a corresponds to negative 2. Okay, and now a is a negative value. And since a is negative, that is, since it is less than 0, okay, you're going to have the graph is going to open down from the vertex. Okay, so in this case, the vertex is going to be the high point. So this will be the location of the maximum. Okay, so you have a at negative 2. Now in terms of what we have with h and k, again, h is going to be the 0 of the binomial, x minus 4. So I have x minus 4 is equal to 0. And so we're going to have for the h value, that's going to be the x value of which we have x minus 4 equal to 0. So we have h is equal to x is equal to 4. And again, we have with the k value, we have the k value is equal to negative 4. And so for what we're going to have here in the vertex, okay, so the vertex hk is going to be at 4, negative 4. All right. And so going back to the line of questions here, okay, and it says, first of all, does the function have a minimum or maximum value? In other words, is the vertex going to be a location of the minimum or the maximum? And since the graph is opening downward from the vertex, again, I repeat, vertex is going to be the high point, so it is going to be the maximum. And where does the minimum or maximum value occur? Okay, and that is going to be the h value in the vertex. Okay, so we have x is equal to h is equal to positive 4. And what is the function's minimum or maximum value? That is going to be your y value, or in this case we have the k value at negative 4. So you have y is equal to k is equal to negative 4. Okay, so the function has a maximum, and the maximum is going to occur at x is equal to 4, and the maximum value is going to be negative 4. And just seeing how this function appears So just taking what we have now. And again, so we're going to have the graph of f of x equal to negative 2x squared plus 16x minus 36 to be a parabola. That's going to be opening downward from the vertex. And again, the location of the vertex, we have 4, negative 4. So again, the maximum or the high point occurs at x equal to 4, and the maximum value or the y coordinate is going to be negative 4. So everything in the y value is going to be lower than negative 4. So negative 4 is going to be the high point from a vertical standpoint. Now, for what we have in the case of the next function, okay, we have a quadratic. Once again, this time we have g of x is equal to 3x squared plus 30x plus 77. And we have in this one. We have yet another standard form, so we have g of x again. We have is equal to 3x squared plus 30x plus 77. Again, the layout is in standard form, so I'm going to write this and convert to vertex form. So again, if I look at separating the variable terms, okay, so you have 3x squared plus 30x. Again, we have separated from 77. Okay, and again, in setting up the expression in terms of where I'm going to complete the square, and we have the first term inside the parentheses to be x squared. So I'm going to draw out the leading coefficient 3, and as I factor out, we have 3 times the quantity of x squared plus 10x, and I have followed by the addition of 77. Okay, so again, just double checking, so I have 3 times x squared is 3x squared plus 30x, and again I have 77. And again, re-entering the phase of completing the square. So we have, again, we have the first term in the parentheses at x squared, so I can look at the first order term and take half of the coefficients and then square out. So you have half of 10 is going to be at 5. And 5 squared is equal to 25. And so this number will be added inside the parentheses. So you have g of x equal to 3 times the quantity of x squared plus 10x. We have plus 25. We have plus 77, and I'm going to have to make an adjustment at the end because before adding 25, everything was level with 3x squared plus 30x plus 77. But with 25 added in, I'm adding not just 25, but 25 multiplied by the leading coefficient, in this case, which we have at 3. And so here we have 3 times 25 is 75, so we have with the domino effect created. Okay, I'm adding 75 at the front, and to offset the imbalance, I'm going to neutralize by taking 75 away at the very end. Okay, so we have g of x, and we have is equal to 3 times the quantity of x squared plus 10x plus 25. Then we have 77 minus 75 is going to be at 2. Again, you can double check. Okay, so you have 3x squared plus 30x. 3 times 25 is 75. And then we have plus 2, so I'm back to 77. And now, again, for this trinomial, okay, this is going to be a perfect square. And in the case of the vertex form, so we have g of x is equal to 3 times And again, x squared is going to be the square of x. And again, for the dynamic that was created upon the addition of 25, again, the 25 was formed by squaring out the 5 and the completion of the square process. And so for g of x, this will be equal to 3 times the square of x plus 5, followed by the addition of 2. And looking at what we have with the coefficients. Okay, so here we have that a is equal to 3. And since a is positive, okay, the graph is going to open up from the vertex. And since the graph opens up from the vertex, that means you have from the vertex, every other point is going to be at a level that is higher. So the vertex is going to be the bottom point. So this is going to be the location of the minimum. And in the case of what we have with the determination of h and k, all right, so we have with x plus 5 equal to 0. We have for the h, have h is equal to x, which would be at -5. And for the k value, okay, the k value is equal to 2. And so for what we have here, okay, with the line of questions, and here you had to be careful. Okay, now we have, does the function have a minimum or maximum value? And this time we have, it's going to have a minimum. And if you notice with the line of questions, we have a change in the order. Okay, because here we had the second question, or second part of the first question to be, where does the minimum or maximum value occur? X equals what? But guess what? This happens to be the last part of the second question. And again, we had the minimum value to occur. And again, we had the h value. And again, that was at -5. Yeah. So you have, in this particular case, right, so you have the vertex hk is equal to -5, 2. So the minimum is going to occur at x is equal to h is equal to -5. And that 2 is going to be the minimum value. And that is going to be the middle part here. So you have x equal to h is equal to -5. That's your x value. And for the minimum value, again, that's going to be your y is equal to k. And that is equal to 2. Yeah, so be careful with the order upon which the questions are displayed. And just looking at what we have in the graph, okay, so you're going from a maximum in number 1 to a minimum in number 2. And here, okay, so you have the vertex is going to be the bottommost point. Again, it occurs at x is equal to -5, and the minimum value, this is in reference to the y value again, so that is going to be at 2. All right, so items 1 and 2, okay, we have involving quadratic functions. Now we looked at numbers 3 through 5 the other day. Now for question number 6, okay, this is a multi-part problem, and we have involving in behavior, zeros, multiplicities, where the graph crosses and touches the x-axis, and also looking at the determination of the y-intercept. And we have in the case of number 6, so we have a function f of x is equal to the negative of the square of x plus 1. And we have times the quantity of x minus 1. And just kind of rewriting this. Okay, so we have, again, so you have f of x. Now just mention, okay, so you have like the minus. Okay, so you're looking at, in essence, like minus 1. You have times the quantity of x plus 1 to the second. We have times x minus 1. And the reason I'm rewriting this, okay, is I'm looking at the end behavior. And I don't care to multiply out all the terms, but I need just the highest order term to define, okay, the leading coefficient as well as the degree of the function, so as to be able to determine the end behavior. So you have, with the highest order term, okay, so just looking at what we have here. Okay, so you got the lead off. You have first factor is a constant, and then we have between what we have for x plus 1. Okay, so you're going to take the higher order term, which we have in x. Okay, so you have like negative 1. You have times x, and this will be raised to the second power. And then we have with the third factor. Okay, so you have the higher order term between x and negative 1. That is going to be at x. So you got negative 1. Now the square of x, that's just going to be x squared. And again, we have times x. And so you got negative 1. And then we have x squared times x is going to be x to the third. Okay. So the highest order term is going to be negative x cubed, or just to stress the coefficient and the sign, okay, we have negative 1 x cubed. So again, we have for the leading coefficient, a of n, again, that is equal to minus 1. Okay, so that is going to be negative. And we have the degree of this whole function. Okay, no, I just only took the highest order term development. So I have n is equal to 3, so we have an odd power. And so just compositing together. So you have leading coefficient is negative. And we have that the degree n is going to be odd. Okay, so we're going to have, in the case of the end behavior, okay, so you have a of n is negative, n is odd. Remember, with odd-powered functions, okay, you're going to have up at one end, down at the other. And now, in this particular case, you got the leading coefficient is negative, so think of it like when something ends on a negative note, you have like a downward trajectory. So if you read it from left to right, like it might be off to a high point start. So you have rises to the left. And then it's going to fall to the right. Okay, or just another way of phrasing. You have up to the left, and down to the right. Yeah, so you got your end behavior. So this is going to be what we have in part A. So you got your end behavior. And for what we have in the case of part B, it says to list each real zero according to the behavior of the graph. And it says, and we're looking at where the graph crosses as well as touches the x-axis. And so we have, once again, we've got with our function. Again, just putting this down again, and now I'm going to sort of stress the degrees here. Okay, so we have f of x equal to the negative of the square of x plus 1. We have times quantity of x minus 1, and so that is going to be to the first power. So looking for the zeros, so we have with our x factors. So we have x plus 1 is equal to 0, so we're going to have the x is equal to negative 1. And for x minus 1, if x minus 1 is equal to 0, okay, we have the x is equal to 1. So you have, in the case of the zeros, okay, so can we have x equal to negative 1? We have x equal to 1. And in the case of the multiplicities, okay, so negative 1 stems from x plus 1, which is raised to the second power. So negative 1 is going to have a multiplicity value of 2. 1 stems from x minus 1, which is just to the first. So the zero value of 1 is going to have a multiplicity of 1. And in terms of whether the graph crosses or touches the x-axis along these zeros. Okay, so anything that has even multiplicity, in this case, I have negative 1 with an even multiplicity value of 2. So here it is going to touch the x-axis at x equal to negative 1. And with 1 which has an odd multiplicity value of 1, it's going to cross at x is equal to 1. Okay. And so for what we have in the case of 6, okay, so you have where the graph is going to cross the x-axis. Okay, so just filling in essentially the box here. So that's going to be at 1 where it touches but does not cross the x-axis. Okay, we have at negative 1. And in terms of the y-intercept, so we're looking at the y value whenever x is set to 0. Okay, so setting x to 0, so you have y is equal to f of 0. So we have the negative of the square of 0 plus 1. And we have times the quantity of 0 minus 1. And I'll just work down here. Okay, so you've got negative sign again. This will be like negative 1. 0 plus 1 is 1, and that will be squared. 0 minus 1 is negative 1. So you got negative 1 times 1 is negative 1, and then we have times another negative 1. And so this will come out to positive 1. So we have for the y-intercept, Okay, we have the ordered pair to be at 0, 1. And in terms of what we have here for the y-intercept of the graph of the function, okay, this is just going to be the y-coordinate, so you just fill in with a positive 1. And if I were to graph accordingly, again, for the end behavior of the graph, see if I can squeeze that in. Yeah, so you got the end behavior. Okay, and again, there were only 2 zeros. Okay, so I had x at -1, x at +1, and there was a y-intercept at 1. And again, we have the end behavior have rises to the left, falls to the right. And again, at -1, the graph is going to touch. And at x is equal to 1, the graph is going to cross. And again, you have your y-intercept at y is equal to 1. And just kind of show you the dynamic that's going to play out. And I'll go ahead and show you the graphed out version of this. I can sketch and kind of do it like this. Okay, so you got reading from left to right, so I have to touch. Then I have to go over the y-intercept, and then it's going to start to descend somewhere. And then once I get to x is equal to 1, the graph is going to cross. And again, I'm sketching. I'm not drawing according to scale, but you got touch, go through the y-intercept, and then you have x equals 1. The graph is going to cross. Yeah. There we go. So just looking at what we have here, again, so we have the x-intercepts at -1, 0, 1, 0. You got the y-intercept at 0, 1. And again, have the end behavior up to the left and down to the right. All right. And now, we've already encountered the synthetic division, okay, from this particular set. And for the items left over, okay, we have regarding rational functions as well as asymptotes and domain. And we have for the case in number 13, okay, so we have set of graphs, and we have functions f of x and h of x, and it says to choose the graph, okay, which will correspond to the respective functions. And if we look at what we have for f of x, okay, so looking at what's going to be the graph of f of x. Okay, now say if I start out with f of x, is equal to 3x plus 6. And again, I have all over x squared plus 2x minus 8. And again, just keep in mind, okay, so we got with the function, I'm looking for the domain. So I have x squared plus 2x minus 8 cannot be 0 in value. Okay, so just kind of do a little bit of shorthand here. So x plus 4 cannot be 0. So x cannot be negative 4. X minus 2 cannot be 0. So x cannot be 2. Okay, so you have for the domain, you have values of x less than negative 4, those values of x greater than negative 4, and less than 2. And we have those values of x, okay, greater than 2. And just looking at what we have and seeing if this function can be reduced or not. Okay, so we got 3x plus 6 all over x squared plus 2x minus 8. And if we look at the factored form, we have 3 times the quantity of x plus 2. We have all over, once again, x plus 4 times x minus 2. Notice that we don't have x plus 4 or x minus 2 present in the numerator, so there's no canceling. So x plus 4 and x minus 2 remain. Okay, so we're going to have vertical asymptotes, where these restricted values will define those vertical lines or boundaries. So you have x equal to negative 4 and x equal to 2. So we have just from what we have regarding vertical asymptotes. So we can sort of begin a process of elimination. Okay, so again we had x equal to negative 4 and x equal to 2. And if you notice for the first graph, we don't have an asymptote vertically at x equal to negative 4, so A goes out. B, we have negative 4, x equal to 2, this stays for now. Same thing with C. And we have the vertical asymptotes negative 4 and 2 for D, but we don't have them for E or F. Okay, so right now it could be B, C, or D. And we have for the next phase, okay, sort of the next part of the litmus test. Okay, and we have coming down to degree comparisons. And it's going to mention, okay, so looking at the degrees, so you have for 3x, okay, the x in 3x being the higher order term in the numerator, the degree is going to be at 1. And then we have x squared as the highest order term. We have the m is equal to 2. And we have that n is less than m. And whenever n is less than or equal to m, you're going to have a horizontal asymptote. And for the less than part, again, the horizontal asymptote is going to be at y is equal to 0. And I think that all of these graphs are going to have the horizontal asymptote. So you have the x-axis throughout. Okay, and now in terms of, okay, so we've gone through the round of eliminating graphs A, E, and F. Okay, after the vertical and horizontal asymptotes round. And then if there's any other process of elimination, okay, this is going to be for the other components we'll be looking into, and that is going to be the y-intercept. so you have y is equal to f of 0. And guess what? So you have 3 times 0 is 0 plus 6. You have all over 0 squared plus 2 times 0 minus 8. Okay, so you have positive 6 over negative 8. So this will be negative 3/4. So the y-intercept we'll have at 0, negative 3/4 on the y-axis. And to see what is going to be played out. Okay, so if you notice for graph B, while we have the same intercepts, okay, as we do with graphs C and D. Okay, if you notice for the y-intercept, this one is a positive value. So it's not going to be graph B because we need the y-intercept to be negative. And we have on the y-axis, notice the y-intercept is above the x-axis, so you have a positive y-intercept, and we need it to be negative, so C goes out. And for graph D, as we have in the middle, so you have 0, negative 3/4, and that intercept is below the x-axis. So on the y-axis, okay, your y value is negative, and so this is going to be the best fit. So for the graph of f of x, okay, this is going to be D. All right. And as for what we have in the case of the other rational function, which we have at h of x, okay, so you have 8 over x squared minus 2x minus 3. And so for what we got, again, for h of x to be defined, we want to have that x squared minus 2x minus 3 cannot be 0. And we have, in the case of factoring, so the quantity of x plus 1 times that of x minus 3 cannot be 0. And if neither factor can be 0, okay, so you have the x cannot be negative 1. And for x minus 3, you have the x cannot be at 3. And for the domain, you have those values x less than negative 1, along with those values x greater than negative 1 and less than 3. You have those values x greater than 3. And in the case of what we have with the rational function, again, so you had just a constant in the numerator. And so you're going to have the factors to remain. So that means that both of these restricted values are going to form the vertical asymptotes. Where we have x equal to negative 1, and also where we have x equal to 3. Okay, so you have two vertical asymptotes. And in terms of, let's say, just looking for any other asymptote, okay, if you notice, you have in the numerator, you have just the number 8, so n is equal to 0 since there is no x term. And we have in the denominator, Okay, so you have m is equal to 2. And once again, between n and m, n is less than m. And so we're going to have a horizontal asymptote, which will again be y is equal to 0. Okay. So just looking at the process of elimination. Okay, so again, two vertical asymptotes at -1 and 3 for x. We have horizontal asymptote at y is equal to 0. Okay, so got -1, 3, horizontal asymptote 0. So A is in the running, B is not. And again, we don't have the right vertical asymptotes for C, and also for D, we don't have that either. So where we had eliminated A, E, and F before to get to the graph F, we're kind of doing it the other way around, where we have B, C, and D are eliminated, and now we have A, E, and F in the running. And now I've already gone through the vertical and the horizontal asymptotes, okay, which are going to be shared by graphs A, E, and F. And the tiebreaker is going to come down to very likely the y-intercept. Okay, so for the y-intercept, okay, so we have that y is equal to h of 0. And guess what? You're going to have 8 over what is going to be -3. So this will come down to -8/3. So we have the y-intercept, okay, at 0 and -8/3. Okay, so again, we have two vertical asymptotes, one horizontal asymptote, and the y-intercept we have at 0, -8/3. And to see how all of this is going to play out. Okay, so you have for A, we have the y-intercept, so you have between, it's like -2 and -3, so far so good. For E, if you notice, we have a positive y-intercept when it needs to be negative, so E goes out. And for the graph F on the y-axis, you have y is barely positive when it needs to be down here. And so A is going to be the only one that is left standing. So A is going to be the graph that defines what we have for h of x. And we have, in the case of our other rational functions, and we have with this last problem, and we have with number 14. Okay, so you have, upon first glance, now f of x and g of x look almost the same because you have like same degrees and all, but just slightly different coefficients among the terms. And so I'm just going to create a little bit of room here. Okay, so we have the first of our functions to look into. So you have f of x is equal to 2x squared plus 2 You have all over x squared minus 2x minus 3. And what I'm going to do here, I'm just going to go ahead and factor. Okay, so from the numerator, I have 2 times, okay, the quantity of x squared plus 1. And for x squared minus 2x minus 3. So we have x plus 1 and x minus 3. Okay, now technically for your domain, again, you cannot have these equal to 0, and your domain will be those values of x less than -1, along with those values x between -1 and 3, and not including either value, and then you have those values greater than 3. And x plus 1 and x minus 3 remain. And so we'll have the zeros of these to define the vertical asymptotes. So you have x equal to -1 and x equal to 3. And in terms of any other asymptotes, again, so you have the numerator degree to be at 2, and in the denominator you have also at 2. And so here we have that n is equal to m. So it's going to be a horizontal asymptote, and this time we have y is equal to the constant that results from taking the ratio of the highest order terms in the numerator and denominator. So from the numerator I have 2x squared, from the denominator I have x squared. Okay, so we have y is equal to 2. Okay, so just looking at what we have in the mix. So you have with the vertical asymptotes, you got -1, 3, y is equal to 2. Okay, so that's good for graph A. For graph B, you got the wrong vertical asymptotes. Got -1, 3, but I got the wrong horizontal asymptote for graph C, so that is going to go out. -1, 3. Nope. Not for graph D either. And don't even have the right asymptotes to begin with from graph E. Now for graph F, got -1 and 3 for the vertical, y equal to 2 for the horizontal. So this is going to come down to either graph A or graph F. And it's going to essentially come down to the y-intercept. Notice in graph A, its y-intercept is positive. And for F, the y-intercept is going to be negative. Okay, so in terms of what we have here, for the y-intercept, so that y is equal to f of 0. Okay, so I'm just going to mention okay, so this will come down to -2/3. So the y-intercept is going to be at 0, -2/3. Okay, and so this time around, okay, we're going to have that. Okay, A is going to go out. Okay, so you have just above y is equal to -1. So for this one, for this function, f of x, okay, you have the matching graph, okay, to come out to f. Okay, so 2x minus 2 all over x squared minus x minus 6. Okay, so for g of x, what I'm going to do here, I'm just going to go ahead and put in the factored form for x squared minus x minus 6. So that's going to be x plus 2 and x minus 3. Now this ratio is already in simplest form. And technically the domain, I didn't go through the round of like what x cannot be, but technically x cannot be negative 2 or 3. Again, the denominator factors remain. And so we have for the vertical asymptotes. Okay, so we have x equal to negative 2 and x equal to 3. And looking at comparing degrees, now we have in the numerator, so we have n is equal to 1. In the denominator, okay, we have m is equal to 2. So we have that n is less than m. So you have a horizontal asymptote at y is equal to 0. So just looking at the dynamics that will play out. Okay. It's got negative 2, 3, but I got the wrong horizontal asymptote for graph A. And I don't have x equal to negative 2 either. Got negative 2, 3, but I got the wrong horizontal asymptote again. Again, C does not belong. And where I have x equal to negative 2, x equal to 3, well, F is not present. And for both D and E, x equals negative 2, x equals 3. We have y is equal to 0. And so it's either going to be D or E. And it looks like the tiebreaker is going to be with the y-intercept. So if the y-intercept is positive, it will go to D. And if it is negative, it's going to go to E. And for what we have in the case of the y-intercept, so you have the y is equal to g of 0. So 2 times 0 minus 2. And 0 squared is 0, minus 0 is still 0, and we have minus 6. So this will come down to negative 2 over negative 6. And negatives will cancel out, and so we have 2 6 is reducible to 1/3. So for the y-intercept, this is where y is equal to 1/3. And so for the function g of x, okay, so since e has a negative y-intercept, that's going to go out. And so for this one, for function g, okay, graph D is going to be the choice. Okay. All right. So graph f corresponds to the function f, and the graph D corresponds to the function g. All right. And now just a couple of quick items. And we have with the added review, and just kind of touching upon what we have, say I had checked off numbers 2 and 3. Say if we look at these functions, okay, now we have regarding the end behavior, zeros, multiplicities, the y-intercept. And for 2, now this particular function is given in factored form. Okay, so you have 3x squared times the quantity of x plus 5 then we have times, okay, the quantity of 3 minus 2x raised to the third. Okay, and upon looking for the end behavior, okay, so I can once again look for the highest order term. So just for the components here, okay, so you have as a standalone term with 3x squared, okay, that'll be our first factor. Then from the second factor, we have the higher order term to be at x. Okay, now with 3 minus 2x, okay, I don't have the terms in descending degree order. And between 3 and negative 2x, now the higher order term in this expression is negative 2x. And because this factor is cubed, and we had to consider the exponent 3. Okay, so for the highest order term, so we got from the first factor, okay, so just having standalone, so you have 3x squared. And then we have from x plus 5, the higher order term is x. Then for the last factor, I have negative 2x. And since that factor is cubed, then we have to do the same thing to negative 2x. And so I'm just going to bring this on down. So we've got 3x squared times x. Now for negative 2x to the third. Now, like negative 2x times itself. Like negative 2 to the third is going to be negative 8. And the cube of x is going to be x to the third. And here we have 3 times negative 8 is negative 24. X squared times x is x cubed. X cubed times x cubed is x to the 6th. Okay, I'm not interested in any other term. Okay, and just multiplying, if I were to multiply everything out, your highest order term would still be at negative 24 x to the 6th. Okay, so we got with the leading coefficient. Okay, so we have minus 24. Okay, so that is negative. And we have for the degree n, okay, so we have n is equal to 6. That is even. Okay, and again, if the degree of the expression is even, then we had the same behavior on both sides. Okay, either up at both ends or down at both ends. And since the leading coefficient is negative, this is going to signal that the end behavior, you have down to the left and down to the right, or false to the left, false to the right. Okay, so you got the end behavior. Now for the zeros and their multiplicities. Okay, so for zeros and multiplicities. Okay, so again, I'm just going to stress the degrees here. Okay, so I have 3x squared equal to 0, and I divide by 3. So we have x squared equal to 0, and with the square root property of equality. And guess what? There's no such thing as a positive term or negative term with 0. So x is just plain 0. Now for x plus 5 equal to 0, so we're going to have x is equal to negative 5. For 3 minus 2x equal to 0, okay, so if I isolate the x term, I have negative 2x is equal to negative 3. So we have negatives to cancel out, so x is going to be 3/2 or 1.5. So you have, in the case of the zeros, okay, so I have 0, negative 5, as well as 3/2. And for the multiplicities, okay, so 0 stems from the first factor, which is raised to the second degree. Negative 5 stems from x plus 5, which is raised to the first. 3/2 comes from 3 minus 2x, which is raised to the third. And in terms of whether the graph is going to cross or touch the x-axis along each 0. So 0 has an even multiplicity. Negative 5 has an odd multiplicity, so this graph will cross at x equal to negative 5. And with 3/2 with an odd multiplicity, okay, the function is also going to cross at x is equal to 3/2. And for what we have in the case of, for the y-intercept, okay, so this is our function. So you have the y is equal to f of 0. And guess what? So we have 3 times the square root of 0. Guess what? 0 plus 5 is 5. And you have 3 to the third. Okay, so that's going to be 27. And guess what? Because you got 0 squared, it's going to be 0. The result is going to be 0. So the y-intercept is going to be at the origin. And in terms of just sketching, okay. So again, we have with our zeros, so you have 0, -5, and 3/2. Again, just putting in points here. Okay, so we got -5, 0, and 3/2, which will be between 1 and 2. And for what we have in the case of the end behavior, we have falling to the left and falling to the right. And for what we have along each 0, so we have to touch at x equal to 0, cross at x equal to -5, and also cross at x equal to 3/2. Okay, so we have just for the pattern. Okay, so we have to cross from below to above, and then it's going to descend. And instead of crossing at the origin, it's just going to touch. And it's going to rise up again, and then once we get to x equal to 1.5, okay, we'll have the graph to cross the x-axis. Now I'm not drawing according to scale, but again, you have at the ends, you have to fall to the left and fall to the right. And again, at the zeros, you have crossing at -5, touching at 0, and crossing at 3/2. And then we have for this remaining item, for the quotient and remainder. So here we have 2x plus 4 into 4x to the 4th plus 2x squared plus 6x. And let's see. Again, I normally like to go with synthetic division, but again, the divisor, even though it's linear, it's got that coefficient 2 that is out at the front. So in terms of synthetic division, I'm looking at having to kind of hit the brakes on this one. Now for the polynomial dividend, notice we have a missing cubic term. So we need 0x cubed, so I have 4x to the 4th plus 0x cubed plus 2x squared plus 6x. And I want the dividend to close out with a constant. And since there's no standalone number present without the x attached, I'm going to use 0 for the placeholder once again. So looking at what we have, taking 2x into 4x to the 4th, this will go 2x cubed times. And we have with distributing, 2x cubed over 2x will be 4x to the 4th. 2x cubed over 4, so this will be at 8x cubed. And we have distributing subtraction. 4x to the 4th goes out. And we have 0 minus 8x cubed, so we have -8x cubed. Other terms have been untouched, so we'll just go ahead and bring these down. And we have 2x into -8x cubed. This will go -4x squared times. And distributing, so we'll have -8x cubed minus 16x squared And again, distributing subtraction. Again, line division, you have row by row subtracting. Now we got 2x squared, and what's going to be plus 16x squared, so there'll be 18x squared. And bringing down the 6x and the 0, so you have 2x and 18x squared. This will go 9x times. And distributing, so I have 18x squared plus 36x and deducting, so we have 6x minus 36x, so this will be a negative 30x, and 2x will go into negative 30x, negative 15 times, and distributing, we have negative 30x, negative 15 over 4 becomes negative 60, and subtracting once more, and we're going to have the 30x's or the negative 30x's to cancel, and 0 minus negative 60 will translate to adding, and so it's going to follow that this is going to be the quotient, and as for the positive 60, okay, that is going to end up as the remainder. So the quotient, we have 2x cubed minus 4x squared plus 9x minus 15. And for the remainder, this will come out to positive 60.